Hi, I'm Mai from Omran Cynic X Corporation. I'll be talking about interactive crowd-aware robot navigation by learning to balance the safety-efficiency trade-off in path clearing strategy. In this talk, we're going to focus on the problem of adaptive crowd-aware navigation in densely crowded scenarios. Much work has been done in this field to enable robots to reach a goal without collision with nearby pedestrians. However, when it comes to densely crowded scenarios, the robot easily get trapped into freezing robot problem. As shown in right figure, in a dense crowd, robots tend to freeze, which means they struggle to find a bypass because they unable to find any reasonable path towards desired direction. Or they take unnecessary roundabout way. To overcome this problem, we propose a new approach that assumes a robot agent can act actively depending on the situation. In this work, we aim at developing a framework allowing agents to learn a hybrid policy. Not only to seek a bypass by passively avoiding collision, but also to clear a path by actively addressing nearby pedestrians. In prior work, existing interactive robot navigation focuses only on collision avoidance and interaction with a small number of people. Therefore, they do not work sufficiently in densely crowded scenarios. On the other hand, path clearing interface has been studied in some context. However, the path clearing rule is manually designed. An optimal strategy has not yet been investigated. Here we tackle the problem that, when, and how, robot agents should clear a path, while avoiding collisions. A robot agent may be required to follow the social norm as humans do, but such social behavior is so hard to model explicitly under complex crowd-robot interaction. In this picture, can you guess which is better action to reach a goal efficiently, to move right for finding a bypass, but other agent are approaching from right side? Or to actively clear a path at left side? The challenge is that, there is a safety-efficiency trade-off between path clearing frequency and collision avoidance. While collision avoidance allows agents to travel safely, but too much collision avoidance often result in timeout to reach a goal. On the other hand, apparently, it would be a good policy to continuously clear a path. However, this strategy would not work as expected because too frequent path clearing results in collapse natural crowd flow that increase the potential of collisions. Therefore, our goal is learning to balance the frequency of active path clearing that enables robots to reach a goal safely but efficiently. To this end, we develop a deep RL framework called L2B, Learning to Balance, L2B. The proposed L2B framework enables agents to learn a hybrid policy, choosing either to seek a bypass or actively address nearby persons by clearing a path. Our key insight is that the safety-efficiency trade-off may be viewed as a consequence of social dilemmas between a robot agent and a crowd. Based on this insight, we designed such a dilemma-aware reward function and seek an optimal hybrid policy by deep reinforcement learning. To design a reward function with safety-efficiency trade-off, we leverage the concept of sequential social dilemmas. Social dilemmas deal with situations where individual agents are tempted to increase their own payoffs at the cost of lowering total rewards. In social dilemmas for two-player matrix game, we consider four possible outcomes. R is a reward of mutual cooperation. T, a temptation outcome when defecting against a cooperative partner. S, is a succor outcome for cooperation with a defecting partner. And P is a punishment from mutual defection. They satisfy the inequalities, A, 2, D. Sequential social dilemma is a temporally extended concept of this two-player matrix game with social dilemmas. In crowd robot navigation, they can both move safely and efficiently if they mutually cooperate and give way to each other. While doing otherwise will eventually result in navigation inefficiency or unexpected collisions. Inspired by this, we augmented the reward function used in learning the navigation policy, where the augmented reward function penalizes the undesirable outcomes and encourages mutual cooperation to balance travel safety and efficiency. For more details, at each time step T, a robot agent observes a joint state S that consists of robot full state and crowd partially observable states. Each states include the current position, velocities, and minimum distance between robot agent and crowd agents. But a robot agent cannot observe the desired destination of crowd agents. The robot agent action is designed to have 17-dimensional action space, which is 8 moving directions with and without path clearing actions. With the observed joint state, the agent executes an action based on its policy, and it will receive an instant reward inspired by social dilemmas. In this work, we propose to better balance the navigation safety and efficiency by encouraging the robot to reach a goal efficiently while suppressing incooperate behavior. To incorporate this social dilemma-like structure into RL-based navigation tasks, we augment the reward function to take into account the result of the robot active path clearing. The first term is reward from the environment, and the second term is that from the crowd agent. The environmental reward is given when episodes by reaching a goal or collision with a crowd. In the first term, the robot agent will be encouraged to reach the goal as early as possible, but penalized if they collide with nearby pedestrians. The social reward is given according to the interaction between a robot agent and a crowd agent. The term with beta represents the robot aggressiveness in path clearing strategy, where a robot agent is tempted to clear a path rather than finding a bypass. However, too much active path clearing will harm the crowd flow. On the other hand, the term with eta represents crowd agent discomfort to a robot agent. A robot agent is penalized if it become too close proximity to a crowd, but too much collision avoidance will make the robot travel inefficient. We designed these to have a similar structure of social dilemmas so that the robot agent can be aware of safety-efficiency trade-off in crowd navigation. With such dilemma-aware social rewards, we try to find an optimal policy for the robot that maximizes the expectation of discounted total rewards by deep reinforcement learning. We designed learnable value function that encodes an estimate of the expected return by deep V network, and find an optimal value function by value iteration. In training phase, first we feed 3000 episodes by imitation learning to initialize the value network, whose episodes are collected from reciprocal velocity obstacle models. Then, we train the value network in a reinforcement learning loop via the Atom optimizer. To evaluate the effectiveness of the proposed L2B framework, we develop a simulation environment on top of the OpenAI GIM. One critical choice of designs for simulating interactive navigation scenarios is how a crowd reacts to active path clearing by the robot. In this work, we implement a simplified version of ERVO, which is an extension of RVO considering a person's emotional reaction towards a threat. ERVO simulates how people in a panic choose their paths to safe places or a planned goal in a realistic way. With the simulation introduced above, we evaluate a performance of a state-of-the-art crowd-aware navigation method called SARL, and its extended version with proposed L2B framework, which we will refer to as L2B SARL. Here qualitative results at a glance. As shown in the top right figure, a robot agent trained with collision avoidance only policy struggles to find a bypass in highly crowded scenarios. As a result, due to this behavior, the agent is more likely to time out and unable to reach a desired destination. In the real-world densely crowded scenarios, it would be much more difficult to plan a path with collision avoidance only policy. On the other hand, the down left figure shows that the robot agents trained with our proposed hybrid policy can efficiently but safely plan a path towards desired direction. Yellow-colored circle represents that path clearing action is triggered. Even if the robot agent get trapped into dense areas, the robot agent can easily resolve the situation by path clearing actions. We can see that the agents can effectively leverage path clearing actions, while avoiding confusing a crowd flow. We evaluated the performance of the proposed L2B framework and the baseline under different numbers of pedestrian in a crowd. Gray points represent human agents, and filled orange circle represents robot agents. Bigger orange circle represent path clearing beep actions. While the baseline method tend to take a roundabout way as the number of people is increased. Our L2B framework can stably plan a reasonable path by switching collision avoidance and path clearing. If the path clearing frequency is balanced by our learned adaptive policy, the agent can efficiently reach a goal with the moderate number of times of path clearing. Quantitative results. We also evaluated the performance with the metrics, success rate, collision rate, timeout rate, and average navigation time. Overall, we confirmed that our L2B framework demonstrated high success rates regardless of the number of people n, whereas the baseline method degraded its performance as the environment got more crowded. This is mainly because the baseline agent could only find a bypass passively, resulting in high timeout rates. On the other hand, the L2B provides an significantly low timeout rate thanks to its ability to actively clear a path. In this work, we introduced a new task, robot navigation with active path clearing. To seek a solution for this complex task, we proposed a novel deep reinforcement learning framework that learning to balance the safety-efficiency trade-off inspired by social dilemmas. Our L2B framework significantly outperformed state-of-the-art crowd navigation approach in densely crowded scenarios. One possible direction for future work is to formulate this crowd-aware navigation task in a multi-agent RL problem, where each pedestrian in a crowd also allowed to improve its policy to better cooperate with the robot. Such a direction is beneficial for practical robotics applications such as multiple vehicle control. If you have any interest on this project, please come and visit our project page. Thanks.